the same as when you do your project. First, you have to write a specification for the circuit, or maybe you are given a specification of a system or circuit, and then you do formulation. By formulation, mean you derive the two table or initial equation that define the required relationship between the input. And you optimize to level optimization. But in the previous class, digital electronics, sometimes you will not ask optimize. Optimize could be minimized, could be uh, trying to implement only using certain device. For example, design using ROM, design using marks or CPLD, etc. But if you remember, but bear in mind this time, the amount of component, for example, dates, are not really the issue because our objective from the beginning of the semester is that all the implementation will be implemented or realized in the CPLD. Although because of our situation now, the project, maybe you just do simulation. But the target for the simulation is for the implementation using a smaller version of FPGA, which is the EPM240 CPLD. And then you do the design entry, draw the schematic. So by now, we targeted that not only design on paper, but also design using simulate, design using language code or simulation tool like Waterstone. And then you transform the logic to new diagram, okay, and you verify the correctness of the final design. Okay. Now, the first design is concerning BCD. So why BCD important? Because decimal is our normal, our daily number system that we use. But the issue with the binary coded decimal, when you do addition, assuming that this is also 0110 is a BCD code, 0011 also BCD. When you add 6 plus 3 is 9. It's okay. So this number is still BCD code. However, if you add 0101, which is number 5, with 0111, you come up with 1100. And that is a wrong or invalid BCD code. Because BCD code is binary coded decimal. That means 4-bit binary coding number decimal from 0 to 9 only. So 1100 is actually number 12, and that is not decimal digit from 0 to 9. Therefore, you need to do some correction. So what correction factor you have to do is only when your output above 9. For example, if your number is 1100, what you do is you add 0110. Process is actually, if you remember, from 0 to 9 is valid, and then there are 6 numbers from 10 until 15, which is 6 numbers. Those are invalid numbers. So when you add 6, meaning you jumping. You jumping these 6 numbers so that you go to the correct or valid BCD. So if you look at this one, 1, 2 plus 6 become 12 plus 6 become 1, 2. How do you get that? Yeah. So you do it here. 0 plus 0, 0 plus 1, 1 plus 1 is 0, carry 1, 1, 1 plus 1. So you do the process here. Yeah, your process is the binary part. Not this one. It's confusing if you use this one. And you get 1, 2 in BCD code. So it's just that the tens of the BCD code, you use only one least significant bit. You don't use all the 4 BCD code bit. Yeah? So that's correct now. 5 plus 7 is 1, 2 in BCD. Right? Similarly to the all. You do adjustment once your output is non-BCD. The method for adjustment is by adding 6. And you jump the two table or you jump the invalid list. Now, how do we do it? If you base on this correction factor, then this is kind of the correction factor or the correction method that you do. If you your output when you add, you normally have the carry, and you have the S3, S2, S1, S0. So now you create another output, which is BCD, the H1. This is a binary sum from two BCD input. So you got BCD sum. As long as your input is between, sorry, as long as your addition or sum is between 0 to 9, use, let me do annotation. Wait, here. Now, as long as your output, as long as your output is between, oh yeah, okay. Mouse is button here. Okay. As long as your output is between 0 and 9, that means still within valid BCD, just zero. But if the number is, for example, here, this is number, and number is this. This is 0, 1, 0, 1, 0. This is 10. This is 10. So for 10 is now invalid BCD. Therefore, you add 6. So from this area, you need to add 6 to the numbers here, so you can get the function. For example, 1010 is interpreted as 10. So this must be 1, and with the 10 is 1, and the 1 is 0. Are you following? So for this is what you did in the first video here. Then go back. So what do we do? You have to design the correction circuit. So what is this? Okay. Here. So the correction factor, if you look at the previous, what it says is that your K will be 1. Your K will be 1 as long as your CI is 1 here. C is 1, or what? Or if the numbers is greater than 9. For example, in 1, 2, 3, 4, 5, when K is 0, the combination here is more than number 9. Okay? Therefore, you come up with this correction factor method. Okay, so when the sum exceeds 9, carry bit is C, carry bit C is 1, or the binary sum is between 1, 0, 1, 0. So you got this, this is the correction factor. So that means when C1, that's the first condition, and the second condition based on S3, S2, S1, S0, if the number is 1, 0, 1, 0, 1, 0, 1, 1, and 12, 13, 14, and 15. Therefore, you come up with this equation. A is equal to C, or S3, this one, S3, S2, or S3, S1. And then you can apply the correction here. For example, when you do 4-bit adder, if you just do the ripple counter or the look ahead carry adder, doesn't matter which one. So remember, this is the formula we get from before. So what you do is assuming that number A and B are BCD numbers. So when you add up, then you have to check for the initial output. The final output is the Z. So if the S3, S2, S1, S0, so the function here, so K is C, or S3, S2 is 1, or S3, S1. So you will come up with 0, actually K. So you have to add with 0, 1, 1, 0. You just put, as long as K is 1, you have to add this one at 6. Otherwise, just leave the number here as 0. If K is 0, That means these are all become 0. So that means the z is only equal to this one. But if the k is 1, you will add 1, you will add 0, 1, 1, 0, so that your sum, your k3, your output becomes BCD, corrected BCD. Okay? If you think that, feel free to stop me, raise your hand. Um, uh, um, Ask me. I see Jason is telling the meeting, right? So that is the first approach. The second approach is if you double algorithm. So remember, this is algorithm. So we are not going to, we're just going to sort of verify or see how it works, but we're not going to design or question much about the algorithm. So once you are given algorithm, especially for undergraduate, actually you just apply the algorithm and testing and verification. So for example, double is another algorithm that do correction, or actually that convert from BCD number into, sorry, that convert from binary number into BCD number. So for example, the method or the step, there are 5 steps that you have to follow. The first one is find the number of bits which hold the biggest BCD output. Now, for example, find the number of bits which hold the biggest BCD output. For example, if n is 4, find the number of bits. The bits must be, if n is 4, n is 4, if n equal 4, that means maximum number will be what? Why is my writing stupid? And so forth. So equal 1, 1, 1, 1, which is, this is in binary, which is 1, 15, 1, 0, 1, 0, 1. So what it means here, the biggest LCD and the biggest BCD is this one. Yeah? Divide the output into BCD column of 4 bits each, we will show later, and shift the binary number 1 bit at a time. So as you shift, you check. If the binary number in any of the BCD column is 5 or greater, you add 3 to the BCD columns. Then repeat until the numbers, all numbers has been shifted. So let's see this one, this example. Here the screen. Okay. This is example. If you want to convert 3F, you want to convert 3F, example 3F, okay, into BCD. 3F, the binary number is 1111, yeah, 11111. This is 3F. How 1, 2, 3, 4, 5, 6. 6 bits. So first you have to decide how many, because as we said just now, no, sorry, this is a 7-bit number. Seven bits. Okay. Okay. Oh dear. I think when you cannot open this my screen. If you open my screen, I cannot undertake. Daniel, why is he leaving the meeting? Ah, what happened here? Why can't I anything? Somebody using the screen? Don't use the screen, eh? Let me just use my screen so that I can explain to you as better. Okay. Now, for example, this one, if the 3F 3F, if you return in binary, you got this one, right? So that means what you do is you shift this one, and of course this one you already predict. You know that the biggest number for 3F is 63, and that requires the ones and the tens. So you have to create this column. And each of this column is 4 bit and 4 bit because BCD is 4 bits, right? So you shift the first time, another one left the meeting. No? So you shift the first one. Now check, is 1 greater than 5 or equal 5? No. And shift again. This is 3. 3 is less than 5, so shift again. And now it becomes 7. So because 7 is now greater or equal to 5. The condition is, if it's greater or equal to 5, you have to add 3. So that's why 7 plus 3 become 1010. And then from that 1010, you shift. So when you shift, this one become 2, so the 1 here coming in. So that become 1. This is 1, the new one. The 0, the 1, the 0, and this one right here. Okay. Okay. Right. And then you now after the fourth shift again, we got number equal to 5. So that's why you have to add 3. So that's why you got 1000. Okay? It's okay. I'm recording this slide. So I think I can share it if your line is not very good. Okay. Alhamdulillah, my line is quite clear. Okay. And then now become 8. Then you shift again. Shift. And this number going in. And then this number going out. So you have only, now this is 1. 1 is less than 5. Therefore, you don't need to add 3. You shift, just continue to shift. And now, there's nothing here. I mean, that's, you stop here. Because there's nothing to shift anymore. So when you stop, this one is 3, this is 6. Actually, you can play around. Amazingly, actually, the first time I saw this double, I'm quite surprised how the algorithm is generated. I think somebody is doing PhD to get this one. So this is the process. Yeah. So it is proven. You can do it. Okay. You can do it with any number, and I have done it. So it's up to you to do it. This is in case of 255. If the 255 FF is the binary number, and the BCD number should be 255. That means 2 10 0101 0101. That's a 255. Okay. So this is the process. This is the same as before. So if you shift, you got more than 5, you add 3. This one 5, no, not more 5. Equal 5 or more, you add 3. And then you continue shift. Here 1, you don't need to add 5, add 3. You don't need to add 3, you don't need to add 3. And here you got 7, and now you have to add 3 until you finish. Okay. And the final answer is after the last shift also you have to add 3. Your final answer has to be like this one, 255. In your this is a 4-bit. So the add 3 module basically is we abbreviate it as CADD. So this is a conditional add 3. Okay. So let's say the conditional add 3, you have 4 input, 4 output, whereby you put in binary input, output be either I3. So this number is either the same as BCD input or add 3. So for example, this one, this is the BCD that you implement in your milestone 3. Okay, so you look at this one. If the number is between 0 to 4, So you don't do anything. The output is equal to input. If the number is 5, 6, 7, 8, 9, you add 2. This is CADD. And if the number is bigger than 9, you don't do anything because CADD3 module is designed for binary to BCD. No. BCD correction. So that means you don't take the invalid BCD. You don't take the invalid binary input. Okay? 41. Right. Now, if you remember, I don't know how. Anybody good? Why? How to hide this thing? Right. If you look at it, so you have three D3, D2, D1, and D0 that you need to. So normal digital, you do K-map. You do K-map for D3, D2, D1, D0, and you will come up with D0 equal to D3, B0 bar, B3 bar, B2 bar, B0, plus B2, B1, B0 bar. And this equation is actually in your textbook. Yeah? But the textbook doesn't show how you got it. But actually what you do is this is from K-map. Yeah? Normal procedure. You do K-map for D3, you do K-map for the D2, and you do K-map for D1, you do K-map for D0, and you come up with this equation. Once you come up with this equation, then you can draw the circuit. This is, for example, 6-bit, 6 binary to BCD. And don't ask me how. So this is actually based on the design. The design I noticed is that you always put 0 in the beginning, and then you list all the maximum inputs. So you put CADD for the first 4, for example, you put the CADD module, and then shift another module for CADD, and then shift another CADD. But you know, if your input is 6-bit, what is the biggest number? 6-bit. 3F, right? 63. So the for 6-bit is 3F, and 3F is equal to 63 BCD. In other words, these are the input. The input is actually 6-bit. You have to put 0. This is exactly in one of your in your module 3 when you have to do binary to BCD conversion, and then you go for display. Correct. Because I think I've been discussing a lot with Shazwan and Muslim. I end up doing it myself. Okay. Now, how you improve? No, once you get the module in your book, you have. So for 4-bit, let's say if you just only deal with 4-bit, that means you deal only with this 4. This is 0, 1, 1. Sorry, 4 here. That's 4-bit. That is your master tree, and therefore, for the 4-bit, you only need one CADD. Once you finish, you don't need this 2 more CADD in your design. I will check your report. I think it's due yesterday, right? Right. And improve BCD. In other words, rather than this is better design than before. Can anybody say? Can anybody explain to me why is this better than this one? This is also converting binary to BCD. This one kind of better. You add BCD, but you use the CADD module or the what is it? Conditional add key, and you will get BCD Adder. Right? You can get. So what is the best? Why is it better than before? Oh my goodness.
Last component.
I forgot to record. Right, now I'm recording. Why is it better? Less component, yes? Because you use only one 4-bit binary adder, and then you apply the CADD. This, how you apply this one is based on this rule, right? So that means you got the CADD and you get the output. K can only be 0 or 1. For example, when you add, if your input is if your output is 1001, which is number 9, So the output will remain 1001. But if your output here is, for example, 1010, that means this one CADD3 will convert it to be 0, 0, 0, 0, and here will be 1. It becomes 1, 0 in BCD. Okay, that's what happens. So doing CADD3 module is much better than the other version. Now, the second case study is barrel shifter. Why is a barrel? Barrel mean rather than shifting one bit at a time, you shift a barrel at a time. Barrel means n bits. So for example, you can shift 1 bit, you can shift 2 bit, or you can shift 3 bit at a time, 4 bit, and so on. So the top level view of this barrel shifter is like this. You can shift. So if your n is, for example, 4, not 2, or 4 is 2, you can have up to 2 shifting. And this is your mode selection. This is example. If you want to shift, this is actually a clever way of shifting. When you have the mode selection, that means you have the choice of shifting only no shifting this time. If the selection mode is 0, 0, 0, then you don't shift anything. That means the output Y7 until Y0 will be exactly as the input X7, X6, X5, X4, no shifting. But if your mode is 0, 0, 0, 1, so shifting 1, that means what happens is that X0 will shift to X1, X1 will shift to, Y1 will receive X0, Y2 will receive X1, Y3 will receive X2. Like if you have the annotation a little bit, that means this is the shifting one, right? You got shift, 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 only one bit. If you select 2, means 0, 0, 0, 1, 0, that is 2. That means from 0, 1, 2. So that means you shift 2. So from originally X1 is here, but after shifting 2, X1 will go to where? Not here, 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 but at the position of 1, 2. Y3 will receive X1. And if you set here to be 1, 1, this is like programmable shifting process. So if it's 7, meaning now, at the same time it rotates. So what happened, once you shift, 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 for example here Y6, then what happened to X7? X7 will be rotate back to position Y0. Yeah? So this is like shift and rotate. You don't lose any information. So if it's 7, that means 1, 2, 3, 4, 5. How do you get Y7 here is 0? That means the initially what S0 is here 1, 2, 3, 4, 5, 6, 7. So 7 times we shift. So that means S0 originally here, end up will be here in 1 if instantly, because you use multiplexer. Inside this battle shifter is just combinational circuit, no clock involved. Instantly, instead of shift 1 or 2, you shift 7 bit at one go. And the implementation, let me delete the annotation. So implementation is you require for 8 bit. If you implement using 8 by 1 mux, you require sorry, but let's me finish this one. So you will need 8 mux, 8 units of 8 by 1. So how you arrange? Okay, how do you arrange? For the Y0, if you notice, the pattern for Y0, you look at here. Where is Y0? Here, right? The pattern here, just follow this one. That means Y0 is starting from here, this is the 0 position, x0, x7, x6, x4, and then there's some missing, x3, x2, x1. So yeah, that's this pattern. Actually, you put it here. For x6, for example, we don't have sample of x6, but look at x7. So there should be how many multiplexer here? In between here, you have y1, y2, y3, y4, y5. That's another 5 multiplexer. And then y7, for example, how you arrange the input? This input is following this pattern. Is following this pattern. Following this pattern. Yeah. Somebody is playing with my screen. I don't know. So you look at it. This is again 0. So therefore, the position 0 is x7. Position 1 is x6. Position 2 is 0, 1, 2 is x5 until position here is x0. Position 0. So the arrangement of the data for your marks is left is 0, right is 7. Starting from the left to right. Yeah. All right. Okay. So I actually prepare the sheet for 4-bit. 4-bit. Sorry, what? This is 8-bit barrel shifter. Actually, I want to do 4-bit barrel shifter, but I think I just skip that. Let you do it. Okay, I skip this one. Now you can also implement the same function just now by using 2x1 marks. This is the first approach. However, the first level require now the whole thing here. The whole thing here is only for y7. Yeah? So that means for y6, we have 1, 2, 3, 4, 5, 6, 7. 7 marks 2x1 need to generate y7, and you need another 7 for y6, another 7 for y5, and so on. So end up, you require how many? End up you require 7 times 8, 56 2x1 marks. Okay? 76. This is another approach. This is a better, clever approach using logarithmic 8-bit barrel shifter. So rather than using 56 just now, you arrange it this way, still doing the same function, but now you use 1, 2, 3, 4, 5, 6, 7, 8. You use 8 times 3. So you use only 24. Okay, so this one you use only 24. I think I leave it. Yeah, because it takes time to explain. It can be explained. If you want, you can discuss one-to-one in this one. Yeah, but you can trace. For example, you put here 0, 0, 0. That means what come out here will be 0, will be 0, will be 0. So that means here x0 will come out, and then the x0 will come out here, so y0 will put x0. If you put 0, y0 will be 0. Let's say if it's 1, 1, 1, 7. 7, see 1 is 1, this is 1. So that means the output for this one will take x6. The output of this one will take, try to trace, x4, and so on. Yeah, this is quite nice to do it, but you need a few colors, and you can do your own tracing. Yeah, this online thing is difficult. If you are face to face in the class, I will show you. It's too difficult for me to show you on this online. Plus, the line, the longer we have the lecture, the more money you pay for your internet, right? Government give you only 1 gig free, but that's not enough actually. Right, let's go for next one. I think next one is next one is comparator. So we call it magnitude comparator because A and B is only assumed as magnitude, positive number. No negative number here. Yeah? So if you use like this, that is for your project, you may use IC. What IC is that? I think I told you here. 7. My annotation. You can annotate annotation. Can I share it? Okay, this one you can use IC 7485 yang saya informal thinking. Why am I on this please? Somebody trying to annotate for me? Right. Here, this is you can use IC 7485 in your project. This is a comparator, normal comparator, 4-bit magnitude comparator. So what happened is that if A, for example, 7 and B, for example, 5, so now A is greater than B, so A greater than B, this one will be turned on, this one will be 0, this one will be 0. If, for example, you change the okay, if, for example, here is 0, here is 5. Now, B is bigger than A, therefore, your B greater than A, or A less than B. Now, the reference, that's another thing. Your reference is always A. In this case, 0 and 5 is A is 0, B is 5. Yes, A less than 5. That means this one will be turned on and the rest will be off. Okay, not off, that will be 0. Okay. Now, the equation is actually, now if you remember your Boolean algebra from last subject, for A equal to B, the equation that means for A equal B, x3, x2, x1, x0. What is x? X is actually AI. For the condition of A equal B, A3 must equal to B3, A2 must equal to B2, A1 must equal to B1, and A0 equal to B0. Okay, I'll just finish it quickly. Yeah? This is I think the last topic. The rest I think you study on your own. Yeah? Now for the X is actually equal to AI exclusive no BI, which means AI BI or AI BI bar or their exclusive or complement. Yeah. So for example, if the function is for less, if A is less than B, what is the condition? A is kosong. You starting from the MSB. Oh, now if you start from you have to start from MSB when you compare. So if you want to know A3 less than B, check for the most significant group. If A is 0, B is 1, obviously A less than B. If A is 1, B is 0, you don't need to look for the rest. You know that A is bigger than B. That's how you do it. But if this is not true, you check for the second part. I mean, if A3 equal B3, then you check for the A2 and B2. If A2 is less than B2, then A is less than B. Similarly, if that is also not true, we check for X3. If X3, wait, what happens is X3? If A3 equal to B3, A2 equal to B2, then you check for the condition of A1, B1. And finally, if A3 equal B3, A2 also equal to B2, A1 also equal to B1, then you check A0, B0. If A0 is 0, which is A0 bar, and B0 is 1, then obviously is A less than B. So the process is the same for greater than, it's opposite. Yeah? Greater than, that means if A3 is 1, B3 is 0, you don't need to see the rest. Obviously A greater than B. If A3 equal B3, then you have to check A2 and B2. If A3 equal B3, A2 equal to B2, you check A1 and so on. So at the end, the equation for the circuit for the circuit for A equal B is simply X 0, X 0, X 0, X 0. So this must be equal, this must be equal, this must be equal. Equal means 0, 0 is be 1, 1, 1 is be 1. This one also either 0, 0 or 1, 1. So you come up with this circuit. Okay. One to the machine. Prepare too much also. Here, a complete one. Now, if you confuse, why suddenly we use this function? If you look at x3, remember what is x3? x3 is a3 equal b3. Just now we said the x no, but if you look at this one, x3 is equal to a3 bar b3, or with a3 b3 bar, and then you not complement. So basically, what you're doing, this part, this circuit is actually this function or this function, same. But it looks nicer somehow. Why? Because you can also generate A less than B, A greater than B, and the rest. Should I explain this one? The best thing is for you to do it. The process is you will compare this implementation is exactly following following this thing, this equation, this two equation, nothing else. Huh? Now, but as you know, in digital system, we don't like to have circuit that like this one 4-bit. We do 4-bit straight. We prefer to do what? Bit slice, right? When you do ripple carry adder, remember? You do 1-bit adder and then you recycle 4 times to get 4 bits, 8 times to get 8 bits. So we prefer to do that approach. So that kind of approach is called iteration or bit slice. So that's what we're going to do next. This one, here. Now, bit slice is actually we want to design a comparator, a single bit comparator, and then we can cascading it. So the approach is you compare A and B, okay, and you label L less than, equal, and greater. But in terms of implementation, actually, either less or greater, you can skip because equal obvious, greater obvious. If the function here is 0, 0, obviously it is less. Now, if you look at this one, if A and B is 0, obviously the equal function. Yeah. If it's 1, 1, equal function is active. If it's 0, 1, meaning A is less than B. That's why this is 1, the rest is 0. If A is 1, B 0, so now A is greater than B. That's why you got this function. So less is basically A bar and B. Equal is actually A bar, B bar. Okay? A bar, B bar. Or AB. Or you use as no. And greater is A greater than B. So again, the implementation here. This is the one before for equal to B. This one for A less than B, which is A bar and B. And A greater than B is A, B bar. This is for 1 bit. If you want to compare 1 bit, A is 1 bit, B is 1 bit. Now, how do we cascading it? Now, comparator is not the same as adder. Adder, when you want to implement, you implement from the least significant bit because you add the least significant bit and then you have to carry out, bring to the next stage, and the next and the next. But for comparator, For comparator, the approach is cascaded model. For the cascaded model, remember, the half adder you cannot cascade because we have carry in, we don't have carry out to connect to the next stage. So for the cascaded model, you assume you have E in, G in. So E is equal input, G is greater than input from the higher significant bit position. I have one. Yeah, very true. Okay. Right. So if the input is 0, 0, meaning the previous, that means, and the AI and BI, we don't know. I don't care. What it means is that obviously A is less than B. 0, 0 is actually the function for less. If the previous one is greater, then regardless of the AI and BI, it means this is like, for example, if you have 2 bit, 2 bit meaning this is A0, B0, this is E for the 1, you compare A1, B1. Most, yeah, A1, B1, the most significant bit. So if the at level of the most significant bit, you already know that the number is greater, and you don't look for the less significant bit. Obviously, is greater. If the previous state is equal, that is when we want to start seeing. For example, if A3 equal B3, how do we know is A greater than B? Then you check the status of the next. If it's 0 and 0, obviously it is equal. Because if you notice this one, you have only equal and greater. Right? Equal and greater. So this is obviously equal. 0 and 0. Equal. If input is 1 and G in is 1, 0, and A, yeah, because A and B is equal. That's why function is equal. 1. If previous state, for example, you compare, I'm always stuck on the annotation. Okay. For example, for the second part here, if A equal B, then you look at this one. If AI, A1 now is equal to 0 and B1 equal to 1. So from this one, obviously, the most significant bit is equal. Then how do you know? A is 0, B is 1. Obviously, A is less than B. But less than, supposed to be then another column. But because you don't have the column for less, you have to give 0 and 0. So inherently, what it means is that the function is less. This is less. Okay? So if A, if it's equal, previous most significant bit is equal, then if A is 1, B 0, obviously A is greater than B. B bigger. Okay? A is A bigger. But if A1, B1, now it go back to the equal function. Yeah? So that is how you interpret. So from this interpretation, you come up and I think because the system is slow, I want to clean the whole thing. Okay, can explain them. Okay, let's do the next one. So in other words, you come up with the equation like this. How do you get this one? E out is equal to E in. I think G out. You just do the K map. Just do the K map. For the E out and G out, you come up with this equation. Okay? and G out is this equation. That means if E in, the input from the previous one is equal and the present one is equal, therefore your E out is equal function. If your previous one is greater than the next one, you check the E in. If E in is 1, and will be 1, 0. So that means A is 1, B is 0. So this is greater than function. And from there, you come out with this one. So that means this start, this one is, you must set this one, set. In order for it to function properly, this one you have to set to 1 and 0. Easiest one is you set it to 1. Now, for example, if this is 1, 0, 1, 2, 1, 0, 1, 0. So what will be the output? How do you know the output? Here. So that means this is what it means is that I have A equal 1, 1, 1, 1, and I have B equal 0, 0, 0, 0. So obviously A A greater than B. The answer is here. G will be 1 and then 0 will be 0. So because for comparator, you only have one output activate at the same time. No, at any time only one output. So either, so if you got 0, yeah, you want to ask something? This one, if you don't read properly, you get confused because you always have to start from the most significant position. When you arrange this one, you have to do it. This is like if you do when you implement your quarters, you implement one big complement and you cascading, and then you have the 4 input for A, 4 input for B, but this value you have to set. This is like the control input. Input here you have to set 1, 0, and this is your output. So if your output is 0, 1, meaning A is greater than B. If it's 1, 0, mean A equal B. If it's 0, 0, it means A less than B. That's how it works. Okay, and I think that's all I can share with you. There's one more actually, but I think it's too simple for you to do that. You can do on your own. The next one is actually look at it. Dia lagi ni. The one incrementer. Actually, you can use full adder, but that is actually overkill because full adder means you have A, B, C, E, sum. So you can just use half adder because all you want to do is y is equal to x plus 1. So you need only one input variable. You don't need like A plus B plus 1. If you use full adder, then one of the input you have to set to 0. You just need only one. Therefore, half adder is better than full adder. Plus, half adder is more than circuit than full adder, so you use half adder. But you set the C input or C0 as 1, so that let's say if you start from 0, 0, 0, 0, and this is 1, so that means it will be 0 plus 1 is C will be 1, and then here will be 0, 0, 0. And then if you do like, if this is for example anyway, if this is 1, this is 1, this is 0, this is 0, then what will be the output? The output will be what? 0 plus 1 is 1, and no carry. So this is no, sorry. 1, 1, 0, 1, 2, 1. So this one no carry will be 0. So 0 plus 0 is 0. Is still 1, is still 1. So that means 1, 0, 0 plus 1 is what is number. So all the time it will be implemented. For your milestone project, you need a register. register with the incrementer. That's what you call accumulator circuit. So that the data that you have on this one, for example, you save it in the register, and then you feed back to the input, so that the next clock, what you do is like x next x is equal to present x plus 1. Now, but this topic is under sequential. That is next chapter. Okay. The next chapter, I tell you, even if for this chapter, digital electronics and digital system are two different things, you have to simulate in order for you to understand better. So from now onwards, so this is no longer simple circuit. This is already systems. We're talking about system. You have to start to focus a lot. Okay. So that's it for my lecture today. Next, after this, what you can do is there's an exercise at the back there, and I will suggest a few questions that you should do. So maybe I will collect some of the final exam questions that related to this topic, and I share with you. And I suggest you work in a group so that I don't want to see too many answers. I don't have time for that. I've got enough problem to study this online thing. So like you have 15 groups, maybe I give two groups one problem, and you solve it, and you share on tablets, or other people that do different questions can share your solution. Will that be okay? You have no choice, eh? That is the learning process you have to do. And you simulate. From simulation, you know the answer. Is correct or not. Okay? So that's all for today. Thank you very much for your patience. I'm sorry that you have to cost money for your life. But I think for this week, this is the only life that we're going to do. The rest we just do problem you want to make you understand on the material, plus some of you who are not here to understand. So if you missed out, or if any of your friends missed out, let me stop here, and I stop recording as well. Okay. Let's go to the chat room. I stop here. Stop sharing. Okay.